This is Math 31, which is an introduction to calculus. And we are looking at limits in Chapter 1, and we're in Section 3, where we're going to focus on one-sided limits. We're going to do two videos, I should say, on this lesson. The first video is going to do a deep dive into a very rigorous and initially confusing definition of a limit. And then the second video will get more into one-sided limits. So for this first video, this is material that you don't have to know for this course. It's pretty deep. But the purpose for going through this definition is to help you in your future studies in mathematics courses where you may see definitions kind of like this. So hopefully this will help set the stage a little bit for your future learning. Well, let's have a look at this definition. We have the statement, if, well, let's kind of look at these keywords first. If blah, 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 then. Okay, so this is a conditional statement. If this condition is true, then we can reach this conclusion. The conclusion is that the limit of this function as x approaches a is equal to L. In other words, this limit exists as x approaches a. So this is the definition of a limit. Let's get into this part. If for any epsilon greater than 0, so this is a Greek letter epsilon. It's kind of similar to our English letter E. So for any epsilon means that we can choose it. So this is like our independent variable in a sense. There exists a delta, another Greek letter. So if I can choose something here and then find something there, so this would be the responding or the dependent variable. So if for any epsilon that's positive, there exists a delta such that these two absolute value statements are true, then the limit exists. Well, let's look at these absolute value statements. Here I have the absolute value of the function minus L is less than epsilon. So I'm choosing an epsilon value here, remember. And if I choose this value, I want to be able to find this delta value that will make this absolute value statement also true. Well, what do these absolute value statements mean? Let's take a little bit of time as we look through these two examples, and then we'll come down to this statement. The 0 is less than the absolute value of x minus a, which is less than delta. So that's from this part of our definition. So these two examples hopefully will help us understand what in the world is being said by this green highlighted part. So you may remember from grade 11 that when we're looking at absolute values, one way to think about absolute values when we have just an x or a linear expression inside is to say that this is describing a distance. So the absolute value in this case is saying this is the distance that x is away from 2. That distance is less than 3. So putting this into words, the distance between x and 2 is less than 3. That's what this absolute value statement is saying. Now, if we visualize that on the number line, then here, the distance is less than 3. So I can go a distance of 3 to the right or a distance of 3 to the left, but my x value has to be within those two distances. Now notice here it's less than, it's not less than or equal to. So I can't equal the number at this end, and I can't have my x equal to the number at that end. What are the numbers? Well, 3 less than 2 is -1. 3 greater than 2 is 5. So what is this statement telling me? It's saying that my x is somewhere between -1 and +5, but my x can't equal -1 because of this less than sign, and it can't equal +5. Well, what if we make a slight variation? As in, here, now at this side, we're saying 0 is less than this absolute value. Again, if I think in terms of words, what that's saying is the distance between x and 2 is less than 3 and it's greater than 0. Well, the less than 3 part we already got from the first example. The greater than 0 just means that our x value cannot equal 2. So if we were to put this on the number line, this is kind of what it would look like, where again, we would have an open circle at this end at -1 and an open circle at this end at +5. So these arrows are just showing the distance I'm going is a max of 3. It's not saying that this is going on to the right forever. It's only going as far as these two values. So my x could be negative 0.8 here, or my x could be 1.99999. My x can't equal 2, but my x could be anything in this interval here as well. So let's just replace these numbers with variables in this third statement. So now we're saying the distance between x and a. So a is some x value, some value on the number line, and we're saying that the distance between our variable x and that value a is less than delta, some mystery number that we don't know, and it's greater than 0. So our number line will look similar to what we had in our previous question, but this time I don't know what number belongs at this end. But I do know if I start from a and I subtract delta, oh, there we go, delta, that's what this value will be. And at this end, if I start with a and I add delta, that will be this value. So that's what this statement over here is saying. So let's come back to our definition. If for any epsilon, so I can choose an epsilon so that the distance between the function and some number is less than epsilon. That's like this first number. The distance between the function and some number, so 2 would be the number, the function would be on either side of this. We're saying that that distance is less than epsilon, so rather than 3's here, we could say, oh, these are epsilons. We can go epsilon to the right or epsilon to the left. Since it's a function value, it would help for us to think of it vertically. So we could think, well, we could go up epsilon and we could go down epsilon units. So for any epsilon, where this statement is true, the distance between the function and this number is smaller than epsilon. So if I can choose a number here to make this true, and once I've done that, if I can find a delta that makes this true, the distance between x and a is less than delta, greater than 0, then the limit exists. Well, that's a little bit clearer, but still we can make it clearer. So let's look at it in a graphical way. So here I have some graph, and we will assume that this is a function f of x. So we'll say that this curve here is y equals f of x. I'll just put the f of x up there. We have this question. Well, not a question, but a statement. We want to be able to choose an epsilon so that the distance between the function and L is less than epsilon. So here I'm just saying this is the value L. What's L? I don't know, it all depends on the function. But we're just getting a visual idea. But suppose this is some y value that I'm calling L. And notice up here in our definition that L is the value of the limit. Okay, so that's why that's important. Well, can I choose an epsilon? Well, let me just pick some epsilon value. Here's my epsilon. There we go. So I'm going epsilon units above L and epsilon units below L. I'll just shift that up a little bit. There we go. So I was able to choose an epsilon to get this interval around the L value. So that's the first part up here. If for any epsilon, there exists a delta, we'll get to that, such that when this distance is true, we can also say that this will be true. So we're partway there. We have our epsilon. We want to be able to find our delta. So that's the next question. Can I find a delta so that the distance that x is away from this a value is less than delta? Well, here's what we're looking at this time. I want to go delta units. I'll bring that down here. Ooh, center it a bit. There we go. Delta units in either direction from A. So again, that's the distance between x and A. So x can be anywhere within this interval. That distance is less than delta. Greater than 0, I should have put an open circle here. I didn't, but we're saying that it can't equal 0. So visually, what we're looking for is, can I choose these epsilon values so I get these red dotted lines so that once I've chosen those, I'm able to find deltas so that these green dotted lines fit within those two values that show up from our function. So here I want in between here and there, I want my green lines to fit in between there. And as I've drawn here, it works. So it looks like, oh yeah, this limit exists. But it's not quite that simple. Because in that definition, we had this initial statement for any epsilon greater than 0. In other words, I want this to be a tiny value that's getting closer and closer to 0. So suppose I pick a smaller value for epsilon. I'll shrink this down. There's my epsilon, and I'm going epsilon units above the limit and epsilon units below the limit. Now I look at my deltas. Oh, they don't fit inside. Can I find a delta that would make these two green lines fit inside those red lines? So now I have a point here and a point there. Well, this green line fits okay, but this one doesn't fit inside. Can I find a delta to make this work? Well, I think I can, because I can take this whole thing and I'll shrink these deltas down and I'll get, oh, there we go. Yeah. So now I can get green lines that fit inside the red lines. I can choose an epsilon. Once I've picked any epsilon greater than 0, really tiny, can I find a delta? Well, what if we make this one smaller? Ooh, let's go tiny. We can hardly read that. Do my deltas fit inside? Nope. Can I find a delta that will? Well, let's go. We'll make these really tiny so we can't even read it. There we go. Are my green lines inside the red lines? Yes, they are. Can I keep doing this forever and always be able to find a delta? Yes, I can. Which says that the limit as x approaches a, the limit of our function, f of x, is equal to L. That's what this is saying. So here we have an example of, yep, the limit exists. Well, could we look at a situation where maybe it's not going to exist? So let me just clean up some of this. We'll get rid of those. And we'll say, suppose we had this graph instead. Now, just from looking at this graph, we should know visually that the limit won't exist. And this idea will come out a little bit more in today's lesson, but this gap here is going to be a problem. So we'll get rid of this, and we'll say again, can I choose an epsilon? So here, I'm going to choose an epsilon. Things aren't going to line up spectacularly, but we get the idea. Can I choose an epsilon so that I'm able to find a delta that will fit within these 2 points? So this point and that point. Well, let's see. Let me drag my delta setup over here. And as I put this down here, and I'd say, well, if I was to actually extend this line up here, oh, that doesn't fit inside the red. Am I able to find a delta to make it fit inside the red? Well, let's go for something much tinier, like this. Okay, am I fitting inside? Well, let me just drag this way up there. Oh, looks like I'm almost, but not quite. Well, let's find something a little smaller. There we go. I'm going the same distance on other side of A with these two wee tiny deltas so that I'm able to find in this point here and this point there, I'm able to find function values that put me in between here. Okay, so far it looks like the limit exists. But what if I choose a smaller epsilon? So here I'll shrink my epsilon down, and now we have this. Well, now what's going to happen? This doesn't even hit the function up there. So there's no way for me to find a delta that's going to go inside this red line because it's not going to hit the function. Now you could say, well, way over on the right here, it's going to hit the function. That's true, but what if we had a different function that instead of curving down like that, just kept going up forever? It's not that point over there that tells me if the limit exists, it's these points close by here that tell me if the limit exists. So in this situation, we'd say this limit does not exist because I can choose an epsilon that's wee tiny that takes me to a point where I can't find a delta that's going to fit inside because this upper epsilon here doesn't hit this other function. We could look at other variations of this where suppose, again, my graph curved down here instead of up there. Well, I'll have the same problem. This epsilon is going to intersect maybe over there, but I'm not interested in a point far away over there. I'm interested really close to this point. Can I fit inside the red boundaries? And I can't. So in this case, we would say the limit does not exist. And visually, we can see this gap in the graph. And if we thought left-hand limit is approaching this L, right-hand limit, that comes up more later in this lesson, is approaching some different value over here. It's different, and so we'd say graphically, this limit does not exist. So hopefully that helps understand this statement up there. For any epsilon value, and we want tiny, 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 anything that's greater than 0 and really close to 0, can I find a delta? So that the distance between the function and this L is less than epsilon, whenever the distance between my x and a is greater than 0, less than delta. Then the limit exists. Well, we'll look at an example, and after all that confusion, you'll probably find this example really simple. But here we go. We have this function, f of x equals 5 minus 3x. And we want to show that the distance between the function and 2 is less than 3/100ths if the distance between x and 1 is less than 1/100th. So we want to show that this is true if that is true. So since this is what we want to show, this is where we start. And we'll replace this f of x with the function. What is it equal to? It's equal to 5 minus 3x. And we're going to subtract 2 from that inside the absolute value sign. That's less than 0.03. Well, we can simplify what's inside there. 5 minus 2 gives me a 3. So I get 3 minus 3x inside the absolute value signs. Is that less than 0.03? Well, I want to show that this is true. If that is true. So my goal is actually to get to a point where I have this x minus 1 inside this absolute value sign. And as we look at this, we can see there's a common factor of 3, but even better than the common factor of 3 is to think a common factor of -3. Because if I factor out a -3, then I'll have a -1 plus x inside my absolute value sign. Why is that better? Because -1 plus x is the same as x minus 1, which is what I'm trying to get to up in this statement up here. This is multiplied to -3 inside the absolute value sign, which is less than 0.03. Now let's just take a little detour to the side here for a second. Suppose I'm looking at the absolute value of -6. Well, you all know what that's equal to. But what if I was to think of this -6 as being something factorable, like -3 times 2? Well, the absolute value of -6 I know is +6. But could I separate this product and say, well, this is equal to the absolute value of -3 times the absolute value of +2? Well, absolute value of -3 is +3. Absolute value of +2 is +2, which is 6. So yes, these two sides are equal. So I'm going to use that idea here, where here I have this -3 multiplied to the binomial, and I'm going to separate it into two separate absolute value statements. The absolute value of -3 times the absolute value of x minus 1. Is that less than 0.03? Well, yes, it must be, because we have this statement. What's the absolute value of -3? It is +3, so I can get rid of the absolute value sign. Here, because I don't know what x is, I have to keep the absolute value sign. But now you can see where we're going. Since I have this common factor of 3, I can divide both sides by 3, and my left side gives me the absolute value of x minus 1. My right side, when I divide by 3, gives me 0.01. What was I asked to show? I was asked to show that this will be true if this is true. And I just showed that, oh, look, this is true. That is my last line here, which means this original statement up there must also have been true. It's a little bit of backwards thinking, but that's how it works for this type of question. There will be a few questions for you to try in your textbook related to this, but again, this is not critical for the course. This is just to help us understand this fairly complex definition of what a limit is. That'll be the end of this video. Stay tuned for part 2.